What's going on, smart people? Today is day 2 of grad school. I promise I'm not going to do this for every single day. Doing it for today because day 2 is really part 2 of day 1 because you never have all of your classes on one day. So today I wanted to go over the classes that I had today, go over some syllabus stuff, the course contents, what we're going to be learning. Today I had Statistical Mechanics and Computational Physics. I'm really going to be limiting the detail to the Statistical Mechanics course because, as I mentioned yesterday, I might be taking formally the course in quantum field theory, and if I do that, then I will be pushing computational physics back until this next spring because it's offered every year, and I don't know when the next time second semester quantum field theory will be offered. So if I can take it now, I will probably push computational back until then, and then I'll get into more details about it whenever I come around to taking the class, which will probably be next spring. For those of you who are unfamiliar with computational physics, that might sound like a redundant course. Like, yeah, I compute things all the time in physics. With computational physics, it's like when you want to solve an integral and you type it into Wolfram Alpha or Symbolab and it spits out an answer, how does the computer know what an integral is? How does it know what a sine wave is, for that matter? This course is a course that teaches you the inner workings of how to write a code to solve things like integrals, derivatives, differential equations, partial differential equations, eigenvalue problems in linear algebra. It's teaching you the tools, teaching you the algorithms to implement that in some programming language like C++ or maybe Python or Fortran, whatever your favorite is. You see, a lot of problems in physics are non-analytic, meaning you can't just take a pen and paper and find the answer to a problem. That's why in every single quantum mechanics course around the world, we are all solving the Schrödinger equation for the same potentials: infinite square well, finite square well, harmonic oscillator, delta function potential, and a handful of others, because those are the few ones we can solve with a pen and paper. Now, what happens to the ones that are too hard? What happens to the one that you can't solve with a pen and paper? Those are just things that we don't know how to solve? No, that's where the coding comes in. You can write codes to solve them for you. I mean, if you want to find the area under some curve and you don't know the indefinite integral, there's no one stopping you from taking that area and approximating it by a million different rectangles of the same width and adding up all those areas to approximate the area under the curve. Or you could write a code to tell it what a rectangle is and to add up all of those areas, and it'll do that much faster than you can. So computational physics is an extremely powerful course. Every physics student should have to take at least one course in it. I just might be pushing this back the next year. But let's go ahead and talk about StatMech. I think I've talked about computational for too long. In classical thermodynamics, you're interested in things like equations of state and state variables like pressure, volume, and temperature, and you take a macroscopic look at these kinds of things. You look at how the piston moves up and things like that. You don't talk about the particles really that make up the system. But in statistical mechanics, you see, is there a way to relate these state variables statistically to the constituent particles that make them up? And you uncover the same laws of thermodynamics, and you have more of a statistical interpretation of these state variables like entropy, which is in terms of the natural logarithm of something called microstates. So it's a different approach to the same thing, but can also, in a sense, take you further into things like quantum statistics if you're interested in like pure, mixed states, or different types of gases. So it's a really rich field. There's tons of material. So let's get into the course outline. The first one is a quick review of thermodynamics. Then we get into the principles of statistical mechanics, microstates, macrostates, then elements of ensemble theory, which is like Liouville theorem, microcanonical ensembles, then a whole bunch of canonicals. We got canonical ensembles, grand canonical ensembles, then quantum statistics of pure mixed states, density matrices, theory of simple gases, ideal Bose systems. You may have heard of Bose-Einstein condensates before, ideal Fermi systems, degenerate Fermi gases, imperfect gases, letting the things interact a little bit, phase transitions and critical phenomena, and lastly is non-equilibrium statistical mechanics. In classical thermodynamics, you may have some state of a system, and you normally assume it's in equilibrium, but what do you do if you can't make that assumption? Well, I don't know yet. I'm not at that part. That's part 12. I'll let you know. And that is the course outline for statistical mechanics. I'm pretty excited for the course. I'm more excited now than I was, which is good. Tomorrow I should be getting my TA assignments, which is exciting. Saturday is the qualifying exam, which is not as exciting. Let me know in the comments section. Are you all done with your grad school applications? How are you feeling? How is life? Let me know all that stuff in the comments, and I'll see you guys there.